Sir, it's visible right now, sir. But but it seems some. Sir, is it in the PDF format or PPT format?
I'm using PPT format.
Okay, sir. I think some font has been some. There are some writings where the font has been overlapping. So
Yeah. So let me see.
Good morning. This is Samson. Hello.
yes, sir. Suvin sir has just joined. He has tried sharing the screen. He'll just get back there. I think he was trying to just import it to PDF.
Okay. Okay. Fine.
Suvin sir, is it audible?
Yes, I can hear you.
Okay, sir. So shall we start, sir?
Yeah, we can start. Suvin, good morning. This is Samson.
Good morning, Professor Samson. How are you doing?
Yeah, I'm good, doing good. How are you?
Yeah, I'm great. Actually, I am on vacation. I came to hometown. I'm in Kerala right now.
Oh, I see. Very good. Okay, then you should have visited NATPAC also.
Yeah. So, I mean, I'll try to visit NATPAC. It has been quite long. I have been planning, and even me and Dr. Digvijay were discussing. One day we have to visit and see what all facilities we have, what kind of collaboration we can bring to move forward together. Yeah, definitely.
Sure.
Visit.
You are welcome. But like us now, which part of Kerala you are now?
I'm in Calicut, Kozhikode.
Kozhikode. Okay, Kozhikode exactly.
Vadagara.
Okay, probably you can visit our Kozhikode office.
Okay.
It's very
Sure.
Okay.
So where exactly it is located? Is in the.
It is in CW Ardeng campus.
Oh, okay. Sure.
When will you be going back?
I'll be going back on most probably towards the end of first week of November.
Okay. Fine. We have one program on I think 8th and 9th and 10th at Calicut, two programs.
Okay.
So,
9th and 10th.
Second also.
So
No,
I
second
didn't
also.
plan the return. I have to plan most probably 11th, 12th. I'll be traveling.
Okay. Then, or I think even second also we have a program there. We'll meet someday. No.
Sure, definitely.
Okay. And maybe like let's know that you are three there, no? Transportation people.
Yes, we are three. Me, Dr. Digvijay, and Dr. Ramya. And Dr. Ramya works mostly on pavement materials. And myself and Dr. Digvijay works on intelligent transportation system, traffic safety, and so on.
Okay.
Yeah.
You have an MTech.
Sorry?
Hello. Sir.
Yeah. Okay, in between I got a call. Fine. Audible?
Yes.
Well, I'll talk to Suvin later now. Probably we can start. Shahim, please welcome the gathering.
Good morning to all the esteemed attendees here. I'm Dr. Sunita Vijayan, Junior Scientist at NATPAC from Transportation Planning and Engineering Division. I extend a heartwarming welcome to each and every one of you for joining us today in our TransPedia Research Talk Series. This talk series is yet another unique endeavor of KSCSTE-NATPAC, a mission to explore diverse topics, share knowledge, and foster research in transportation. Here we will be featuring young researchers to share their profound insights for healing the field of future research and development in transportation.
Is called TransPedia Research Talk Series, envisioned to promote research for shared benefits by disseminating knowledge on diverse topics from cutting-edge technologies to sustainable solutions. Desirably, this also brings out a platform for young researchers across the globe to connect and interact to better shape the future of research and development in transportation. The inaugural talk of the series was conducted on 24th August 2023 through online platform, where more than 100 participants from eminent institutions, departments, etc. attended. The inaugural address was given by Professor Dr. Tom B. Matthew, Chairman, Research Council, KSCSTE-NATPAC, and Professor at IIT Bombay. The third talk in the series will be delivered by Dr. Suvin P.Venthuruthiyil, Assistant Professor, IIT Hyderabad, who had completed research under the supervision of Professor Mallikarjun Junju, Department of Civil Engineering, IIT Guwahati. It is with great pleasure and enthusiasm to extend a warm welcome to our distinguished speaker who has graciously accepted our invitation to share insights and knowledge in the realm of proactive road safety analysis. After the presentation, we will have a Q&A section where you can pose your questions and engage in a meaningful dialogue with Dr. Suvin. Feel free to participate actively. Once again, thank you for being here today, and let us welcome our guest, Dr. Suvin P.Venthuruthiyil, as we are eagerly await the insights he is about to share.
Thank you. Thank you, sir, for your cordial welcome note. Now, I would like to invite Dr. Vasudevan N., Junior Scientist, Traffic Engineering and Safety Division, to introduce the speaker to the audience. Please, sir.
A warm good morning to everyone. Today we have Dr. Suvin P.Venthuruthiyil, Assistant Professor from Department of Civil Engineering, IIT Hyderabad. Dr. Suvin completed his PhD from IIT Guwahati in the year 2021. His research focused on trajectory-based proactive safety assessment of road traffic under the supervision of Professor Mallikarjuna Junju. Prior to joining IIT Hyderabad, Dr. Suvin held the role of a postdoctoral researcher at the University of Memphis, USA, in the Department of Civil Engineering. During this phase, his research was primarily centered around cutting-edge areas such as freight logistics, connected and autonomous vehicles, electric vehicles, and work zone safety. The topic for today's talk series is revisiting proactive road safety analysis, past, present, and the way forward. As we know, the road safety has become one of the global societal challenges. The focus is to minimize the occurrence of fatal crashes worldwide as per the Vision Zero initiative. To achieve such a vision, it is essential to know the underlying mechanism of the crash occurrences, which is possible through proactive safety assessment techniques. This talk focuses on bringing insights into the potential of proactive road safety analysis methods for enhancing the road safety. I welcome Dr. Suvin P.Venthuruthiyil to this talk series. Dr. Suvin, over to you.
Hi,
Am I audible?
Yes, sir. Please go ahead, sir.
Yeah, actually I can hear back.
back.
So
So
it's
it's
echoing. Yeah,
Still is there.
Anyway, let's
Let's
see.
see.
Do I need any?
Hello, Dr. Suvin. Hello, Dr. Suvin. Hello?
Suvin sir, is it audible?
Actually, he is unable to access. I will try to contact him.
Yeah. Please. Okay.
Hello. For some reason, I can't see anything. Even
Can you share, sir? Can you share?
Can you share? Please try to share it, sir. Share the PDF, sir. Earlier it was visible, sir.
Otherwise, we will share from here.
yeah, am I audible now?
Yes, sir, you are audible, sir.
Please share your slides.
Dr.
yeah,
Vasan, am I
Yeah.
audible?
Yes, sir, it's coming up, sir.
Fine. So,
No, sir, now it is not. It is not visible.
sorry for the delay. Some technical glitch.
You do once more sharing.
I'm trying to share my screen now. Give me a minute. Yes. I hope you can see my screen as well.
Now, okay.
Yes, sir, it's visible, sir. Please go ahead, sir.
It's clear. Yes. Oh, thank you so much. Thank you so much for that warm welcome and giving me this opportunity to interact with all the participants and the people in NATPAC. So already there was a brief introduction about myself, so I'm not spending any time on explaining that. So this talk is mostly about proactive road safety analysis. Now, without any further delay, let me directly go into the main content of the presentation. So today we are mostly talking about proactive road safety. I hope most of you are heard about what is proactive safety analysis. If not, you might have heard about active safety analysis, where people will be using the historical crash data to understand safety of a transportation facility. So in this presentation, mostly I'll be talking about proactive safety analysis, and the entire talk will be organized as presented here. First, I'll be introducing what is proactive safety analysis. And if you see the proactive safety analysis generally explored in the literature, mainly people have used it for multiple purposes, including assessing the safety of facilities or developing a real-time warning system and so on. So we'll touch upon what are the different goals of proactive safety analysis. And after that, we'll be discussing mostly about active and proactive safety analysis. It is very important to know what is active safety analysis and proactive safety analysis. Once you have clear idea about these two, you would be able to really appreciate what are the potential benefits of proactive safety analysis. And I already mentioned in the active safety analysis, it's about crashes, and proactive safety analysis is something else. So that something else is the conflicts. So you should have clear idea about what conflict is. and how it is different from crash. So we'll discuss a little bit about what are the major difference between crash and conflict and how you can identify conflict from the real field. So one of the widely accepted way of quantifying the conflicts from the field is using surrogate safety measures. Most of you might have used or heard about some of the surrogate safety measures widely used in the practice, for example, time to collision or post-encroachment time. But if you really want to do effective proactive safety analysis that is going to make certain impact on the safety of transportation facilities, you should know what are the desirable properties of a surrogate safety measure. We'll discuss what are those desirable properties and what actually lacking in the literature in terms of evaluating the safety of different transportation facilities using proactive safety analysis, and what is the way forward to improve the proactive safety analysis using surrogate safety measures. After discussing some of the important surrogate safety measures, we'll discuss about anticipated collision time, one of the novel surrogate safety measure developed recently, which has a potential of resolving some of the drawbacks of the existing surrogate safety measures. After that, we'll discuss some of the applications of anticipated collision time to emphasize how we can use this one particular surrogate safety measure to do different proactive safety analysis, which we'll be discussing in the goals of proactive safety analysis. Okay, with this, I'll start the main section of the talk. But before that, let me tell you something. It's regarding if I talk too fast, please feel free to stop me, because I have the tendency to speak too fast, and also I have a little bit cold, so my ears are blocked. So I may feel like I'm speaking loud, but I may not be. So if I'm not audible, please feel free to stop me and let me know if you have any discomfort in terms of hearing, listening me, or if you have any other doubt as well. Yeah. So let's start. Okay. Now, if you see this map, where you can see a lot of numbers displayed on the map of the world, where these numbers indicates the number of crashes happened in the year of 2019 alone. And overall, it was reported that almost more than 1.3 million people die in road crashes every year. And also, as per the global status reported released by World Health Organization, the road safety is a big global health and development problem which needs to be addressed from its root level. And because of this large number, we can even say that the road traffic crashes as the modern killer that is actually impacting the socio-economic aspect of a country or a region. So in order to address this issue, one initiative started worldwide, which is called Vision Zero, which states that it can never be ethically acceptable that people are killed or seriously injured when moving within the road transportation system. Which means that, see, for one person, the mobility is its fundamental right. So when a person, a person moves from one place to another place, it is essential to ensure that he or she would be able to make his trip without any safety hazards. Right? If we are unable to provide the minimum safety, it is a failure of, in fact, the government, the nation, the researchers, the engineers, the designers who actually work on the highway design, operation, and safety establishments. Right. So with that concept, the Vision Zero initiative decided to achieve a goal of, it's in fact a very big goal, wherein by 2050, those crashes are less severe, in part because of changes to how we build road. roadways are designed to reduce speed in safety critical areas and lessen the chance of more severe crash type. Which means that by 2050, we'll try to minimize the occurrence of fatal crashes. Even though if any crashes are occurring, we'll make sure that those crashes are less severe. There won't be any fatalities. How we'll achieve that? We'll make sure that the roadways will be designed in such a way that the vehicle or the driver would be able to, or driver would be informed about the safety critical areas which is there on the network, and he would be able to take appropriate evasive action to avoid any severe crashes. Now, if you want to do that, you should know how a crash is happening. What is the different stages involved in the occurrence of a crash, right? In fact, if you think about the occurrence of the road crashes, it is not a problem that just started few years back. From the day the first vehicle started moving on road, the crash risk was there, and it has been many years, and we are unable to address this issue. If you think about it very deeply, you'll understand that, or realize that it was actually because of the way we approached the road safety. Because for many years we were assuming that, or we considered that traffic death and severe injuries are the inevitable side effect of the modern life. So it is the problem of the public. It is not the problem of the designers or policymakers or the engineers. It is actually the problem of the road users. So that's how we treated road crashes. But later we realized the reality that we can actually prevent the occurrence of any crashes by taking a proactive preventive approaches that prioritizes traffic safety as a public health issue. From this understanding, we started exploring what might be the best way to come out of the issue of road safety. As I already discussed, the goal of performing proactive safety analysis is not only to assess the safety of one particular facility. It can also be used for, but not limited to identify the crash hotspot on a transportation network. It can be used for real-time safety prediction and warning. When we say the safety prediction and warning, it is kind of ADAS system, which a driver can be used in his vehicle, where the ADAS system will be giving the warning to the driver about the safety situation in real time, right? And also it can be used for a fully autonomous vehicle to navigate through the traffic safely, where you can use this information about the safety to predict or planning its path. And the next application of proactive safety analysis is for evaluating the effectiveness of crash mitigation practices, which means that when you apply a mitigation measure or any safety treatment for a transportation facility, you would be able to make sure that your safety treatment is successful, right? It can be anything. It can be some kind of geometric alteration you are providing to improve the safety. You are adding some kind of control measures. You are adding some kind of warning systems. Let it be anything. Once you implement such kind of facilities, you should be able to quantify whether it is really improving the safety or not. How we can do that? So if you are using the active way of quantifying that, the effectiveness of the safety treatment, we have to wait for the crashes to occur for years. Then only you would be able to make some conclusion about whether the applied safety treatment is efficient, effective or not. If you use proactive safety analysis, we would be able to instantly evaluate. When I say instantly, it is not like immediately after implementation. You can collect the data for a few days or for a few months, and you can have a before after study comparison to make a statement on whether the safety improvement is appropriate or not. Now, we already said there are two ways of assessing the safety for a highway system. One is active safety assessment, and the next one is the proactive safety assessment. Now, the active safety assessment is a conventional way of looking into the safety of road facilities. What are the issues we may face if you use this active safety analysis of road facilities? One important problem is you might have observed in the literature, which uses crash data for quantifying the crash risk or the probability of crash, or modeling the association between the occurrence of crash and the other variables. You might have seen that most of the limitation part, most of the studies writing in the limitation part, that they have limited crash data available. So as a statistician, we can make that statement. There is nothing problematic in that. But on a humanitarian ground, if you look into that statement, it states that I'm sad that there is no enough crash occurred, there is no enough death happened to for me to do some kind of safety assessment of the facility, and it's not acceptable. It's not ethically correct, right? So the active safety assessment method actually allows the crashes to happen to do some kind of mitigation for solving that safety issue. And as I already said, it is not ethically correct. Another issue is that we actually depends on the historical crash data, and it has been widely reported that there are so many issues related to historical crash data. You can name it as like there is a problem of underreporting, there is a problem of longer data collection period, there is a problem of kind of all the crash types are not captured properly. You don't have any information about the pre-crash scenario. You have all the information about the post-crash scenario. So there are so many issues reported in the literature related to the historical crash data. So if you take these 2 points itself, it's clearly state that there is a certain limitations for the active safety assessment. But I'm not stating that the approach of active safety assessment is wrong. The approach is correct. It will give you a reliable outcome as well. But if you have sufficiently large, accurate historical crash data, right? And if you don't have that, this method is not appropriate to use. So, what is the problem with active safety assessment? I have already mentioned when we were discussing about the issues related to historical crash data. So this is a nice graphical presentation of the crash data or the associated information about crash occurrences. The historical crash data is in fact the tip of the iceberg, and we have unexplored, unknown information, lot of information that actually leading to the occurrence of a crash. And if you want to really stop the occurrence of a crash, you should be able to understand all the underlying process which is actually submerged, not which is visible on the top. Definitely the whichever visible on the top, the tip of the iceberg is useful. But if you want to break the occurrence of the crashes, if you want to stop the occurrence of the crashes, you should have a thorough understanding, a clear understanding about how this process is occurring, how is this crash generation process is occurring. I'll discuss more about what is crash generation process in the coming slide. But for the time being, the takeaway is that the active safety analysis use only the visible information about the crash, but we have unknown, a huge quantity of unknown information, which is actually going to be very useful if we have the information about that. And in the probability safety analysis, we actually use this information. Now, what are the challenges? If you look into this problem, when I mentioned all these issues related to the active safety analysis and the benefit of probability safety analysis and so on, it is not that easy. I mean, the problem is much bigger than what we think about it, right? Why it is that challenging? Some of the reasons are there is lack of adequate knowledge of the sequence of the crash generation process. How actually crash is happening? I mean, it's not an instantaneous process. Though it is an instantaneous process, it's not like just happening kind of a kind of delta process, right? It's not a kind of a process suddenly happened. It has a series of links associated with this crash occurrence, and each of this link in this particular sequence of crash is important. And our objective as a safety scientist or safety researcher to identify the weak link in that particular process or the critical link in that particular process and break that link to avoid the crash. And priority safety analysis actually allow you to identify that particular critical link and break it, right? So that is the overall benefit of priority safety analysis. Now, the problem is there is a lack of adequate knowledge about what are all those links and how to identify those critical links. And definitely how we are going to identify this critical link is using certain measure which can quantify all these processes, and that measure is called surrogate safety measure. The problem with existing surrogate safety measure is that they can't capture all the possible crash types that can happen in a road system or on a particular facility. And if you see all the surrogate safety measures that is already available, there are so many potential benefits associated with each and every surrogate safety measure, and it has its own demerits as well. So we have to come up with a surrogate safety measure which will capture all the potential benefits of the existing surrogate safety measure as well as something beyond, which is not actually captured by the existing surrogate safety measures. Now, let's try to understand what are the potential benefits of priority safety analysis over the active safety analysis if you use priority safety analysis in a real field setup. So the first point is about safety evaluation possible for new facilities or facilities with no crash history. So, I mean, we have already discussed a few aspects of this. What it says that you have a new facility constructed and you want to know whether the facility is performing well in terms of the safety. Most of the time, if you are using the active safety approach, it is very difficult to do some analysis on new facilities in terms of safety evaluation because we have to wait for the crashes to occur, right? Or in fact, the other example is if you have a facility which is actually performing well in terms of safety, that means there is no any historical crash occurred, but it can be a potential kind of sleeping volcano which can actually erupt one day and have a kind of very severe crashes. So if you don't have crash history, that doesn't mean that the facility is safe. You would be able to see what is the frequency of conflict occurrence, what is the likelihood of a future crash, what is the likelihood of occurrence of a future crash with higher severity. If you want to do all those analysis, you can use priority safety approach over the active safety approach. Excuse me. And also the priority safety approach is a rapid method because we already discussed that the active safety method rely upon the historical crash data. So we have to wait for years to get statistically significant amount of crash data to do some kind of statistical modeling of crash probability or the association of crash with its causal or its independent variables. So if you are using priority safety analysis, you would be able to do a faster assessment of the safety treatment. As we discussed earlier, you would be able to make a faster deployment of safety treatment, and you would be able to evaluate whether the safety treatment is actually performing well or not. Another benefit is about you would be able to make safety assessment of low volume road users, meaning that this state may not be correct in terms of Indian context, but if you think about any developing countries where the traffic is composed of mainly by cars, you can get a lot of crash data corresponding to cars. But if you look into the other mode of transportation, for example, two-wheelers, you won't be able to get a sufficient number of crashes because the composition of that particular mode itself is very less, right? So for those kind of traffic road users, if you want to do the safety assessment, the ASA, the active safety assessment, may not be the right way to do that. And if you are using priority safety analysis, you would be able to make sufficiently acceptable safety assessment. This is one of the very important concept or idea everyone who works in the proactive safety assessment field must know, because most of the time we talk about conflict and crash, or sometimes we talk about evasive action as well. But the entire process, the sequence of crash generation process is important if you want to really solve the problem. It is not about only conflict, or it's not only about the crash. Every instant has its own importance in the process of crash generation. Let's try to understand this particular diagram. Yeah. So this normal driving regime, if you see, it is the normal interactions that you can quite frequently see on the highways when the vehicles move on the highways. I mean, it's very normal, the normal traffic, right? But before occurrence of crash, there will be certain triggering event, the trigger event that actually initiating the process of crash. This trigger event will become a critical event with time if the interacting vehicles are failing to do some kind of evasive action or some kind of control to break this particular link. This critical events will become conflict when it is going to it's going to make this particular sequence in such a way that the probability of occurrence of crash is very high. And once the driver is in the face of conflict, the driver must apply some evasive action, some serious evasive action to avoid the crash. Okay. And at the end of this evasive action, you can see the crash unavoidable. The moment where the crash will become unavoidable. So after this time instance, the vehicle will completely lose its potential to prevent the occurrence of crash, and the crash will happen. And it doesn't mean that the crash that is going to happen is going to be a very serious crash. So based on the extent of evasive action, based on the level of conflict, the level of trigger, the severity of the crash is going to change, right? So you can classify the complete sequence of the road crash occurrence into mainly three phases. First one is the pre-crash phase, second one is in-crash phase, and the third one is the post-crash phase. So pre-crash phase and the portion of in-crash phase constitute the proactive regime of the crash sequence. Okay, and the post-crash phase is totally about the active phase of the safety assessment. Here we'll get all the crash data and associated information from the field to do the active safety modeling. So the proactive phase starts from the trigger event and its end just before the occurrence of crash. That means when the event has become unavoidable crash. Okay, so we are interested about this particular regime. And in the priority safety analysis, what we essentially do is that we'll try to map the conflict information to crash using certain method. there are several methods. It is like a correlation based probabilistic method, extreme value theory based approach. There are so many approaches, but the underlying principle, underlying concept of probability safety analysis is that we project the conflict information into the crash, and we don't need any crash information to do that. So here we said, okay, the trigger event will end up in crash, but to see the frequency of those events, and if we see the hierarchy of those frequency, we can see that the frequency of severe events like fatal crashes are very, very, very less. And also, if you see in fact, the crash itself is the tip of the pyramid, and this pyramid is called Haydn's pyramid, where he said that road user interactions follow a hierarchy ranging from undisturbed passages, which happens here, to up to the crash occurrence, and the tip of this tip is fatal crashes. And from this diagram itself, you can see that the likelihood of occurrence of the fatal crashes is very less compared to the other conflicts or any other encounters, right? So, which means that the ratio, and this is a research finding, the crash to conflict ratio is almost 1:20,000. That means you will observe almost 20,000 conflicts before you observing a crash. So from this, we can say that crash is a rare and random event. Conflict is also a random event, but it is not rare, it is frequent. We can collect this data, and if we can map this information to crash, this is going to give you a lot of insight into the factors that leading to crashes. If you want to, I mean, we already discussed the conflict is the main link in the crash generation sequence, which can be used for predicting the crash likelihood. There have been many definitions for the traffic conflicts, starting from Klebelsberg, who defined the traffic conflict as those involving dangerous traffic interaction. Now the question is whether this definition is really meaningful, or it is going to give you a clear-cut idea about the traffic conflict. So if you see the term dangerous traffic interaction, what is dangerous traffic interaction? It is going to be very subjective, right? So it is not that easy to use this definition to quantify or identify the traffic conflict. And it will involve a lot of manual interventions, because it is going to be someone, the person who is going to collect the data, his perception about the dangerous traffic interaction. So there will be a lot of bias in the conflict information. Subsequently, Perkins and Harris defined traffic conflict as the situation that necessitating evasive actions. That means any situation that necessitating evasive action can be considered as a traffic conflict. Both the definitions are correct. Both the definitions are going to bring you one of the instance in the crash generation process. But if you look into the details, for example, the definition of Perkins and Harris, you can see the evasive actions are nothing but braking, deceleration, acceleration, steering, and so on. So if you see the real field data, you can see a lot of such instances which are the normal maneuvers, which may not be the evasive actions. So how are you going to distinguish between evasive action and the normal maneuvers? That is a challenge here. That means this information, this definition alone is not going to define traffic conflicts. So the next definition is by Amundsen and Hayden. It's one of the most widely accepted definition of traffic conflicts, which states that the traffic conflicts are the situations in which two or more road users approach each other in space and time to such an extent that there is a risk of collision if their movement remain unchanged. That means two objects are approaching each other, and if they are not changing their direction or speed to avoid that conflict, from that time instance onward, what is the time remaining to end up with a crash? So that is the definition given by Amundsen and Hayden in 1977, and which is one of the widely accepted definition of traffic conflict, and it is intuitively and logically true as well. Very recently, Davis and others have given another definition for conflicts, which is the counterfactual probability of defining a crash, that is the probability of obtaining a crash if the evasive action taken by the road users involved were unsuccessful. That means what is the probability of obtaining a crash if the evasive action is unsuccessful. If you compare these two definitions, in one way both are same. Only difference is Amundsen and Hayden defined it in a time scale using the physics of the movements, whereas Davis has used the probabilistic way of interpreting the conflicts. So the point is both the definitions are same, but the difference is coming the way one is the probabilistically we are defining, and the one is in terms of physics. Now we understood what is conflict, we understood what is probability safety analysis, and we said that the conflicts needs to have certain properties in terms of its definition. But how are you going to quantify it? For that, we use these surrogate safety measures. And initially, according to Tarko and others, surrogate safety measures was defined as anything that can be related to the crash. But again, there is an issue with this particular definition that, for example, there are some studies where people have used traffic volume as the surrogate safety measure. Okay, the traffic volume is a macroscopic traffic stream characteristics, and people have used it as a surrogate safety measure because it is related to the crash, right? I mean, as the traffic volume increases, there is a high chance of occurrence of crash. That's a well-known fact. But if we go with this definition, the problem is, for example, the lighting condition has the effect on the road crash occurrence. The weather condition has the impact on the crash occurrence. Then we have to consider all those parameters, and somebody can actually argue and use those as the those measures as the surrogate safety measure. But that is not a correct way of using surrogate safety measure, because if you look into this crash occurrence, the crash is actually a microscopic level process, right? Because it involves one or two vehicles, two or more vehicles, or n number of vehicles will be interacting, and it's going to have end up with a crash. So it's a microscopic level operation, like a car falling or a lane change. So we have to consider any measure that is at the level of microscopic to understand the crash occurrence. If you use macroscopic level information, it is an averaged information. It may not really convey the actual process of crash generation. So there have been many SSMs developed in the literature which have been widely used for identifying traffic conflicts, and we'll discuss some of the couple of very important surrogate safety measures in the coming slide. But one important point here is that despite 50 years of development that happened in the surrogate safety analysis or the probability safety analysis, the concept of crash surrogacy is relatively unclear within the research community, and eventually it has resulted into publishing counterintuitive results. For example, for the same facility, using different surrogate safety measure, they published contradicting results. That means there is a lack of clarity how the probability safety analysis needs to be performed. So the point here is that those who are actually exploring the probability safety analysis or doing research in the area of surrogate safety assessment needs to be very careful about the selection of the choice of surrogate safety measure and the method you are using for analyzing or assessing the road safety. Now, I already said that you have to be very careful about choosing the surrogate safety measures. So what aspect you have to look into when you choose a surrogate safety measure? So these are some of the desirable properties of a surrogate safety measure, which include a surrogate safety measure should have a short observation period. It should be correlated with clinically meaningful outcome, that is crash, and it should statistically and causally related to the crashes, and it should be affected by safety treatment similarly to how it would affect crashes. Meaning, if you apply some kind of safety treatment, and if you do safety analysis, probability safety analysis before and after the treatment, and if you compare the safety improvement meaning the impact of safety treatment on the safety improvement, you should be able to get similar result as similar to how the crash will be, or the safety will be improved, or the crash risk will be reduced. Okay. The next point is it should be markers of crash with a time scale underpinning, which means that it should be one of the links, or it should represent one of the links on the entire chain of crash occurrence, the sequence of crash occurrence. Now let's discuss quickly a couple of surrogate safety indicators, just to give you a brief idea, those who have no exposure towards priority safety analysis and surrogate safety measures. So the most widely used surrogate safety measure in the field is that time to collision. This is the measure which is used in even in the advanced systems like forward collision warning systems, ACC, and so on. So the time to collision is defined as the time remaining to a potential collision if the speed and direction of interacting road user remain unchanged. Which means that what is the time left for a vehicle to go and hit on the leader vehicle if he is not applying any evasive action, steering away or applying brake and so on, right? So the equation for TTC is this. It is the simple physics we are applying here. We are taking what is the gap available between the vehicles and what is the relative speed of the vehicle. The ratio will give you the time remaining to hit this vehicle at the rear end of this vehicle. And here the condition for TTC to be valid is that the vehicle should be in the collision course. Collision course means that the speed of the leader vehicle should be lesser than the speed of the follower vehicle. The next important surrogate safety measure widely used in the literature is the post-encroachment time. So it is the time between the departure of one road user from a point and the arrival of another road user at the same point, which means that, let's say this is the path followed by this particular vehicle, and let's see this is the path followed by this particular vehicle, and you can see both the vehicles are intersecting at one particular point, and it is not happening at the same instance, right? So after this vehicle leaves, and from that time, after some time, this vehicle is coming to this point. So that time instance, the time difference is nothing but the PET. And if you see that paths on this three-dimensional spatio-temporal continuum, you can see it like this. So here is the time axis. So this path is coming like this, and this path is coming like this. You can see this time difference. At this time, this vehicle came to this particular point, and at this time, this vehicle came to this particular point. The time difference is nothing but PET. Similarly, there are many other surrogate safety measures. Some of them are deceleration rate to avoid crash, delta V, extended time to collision, modified time to collision, and so on. I would recommend you to go through some of these surrogate safety measures to understand what essentially these measures capture and what are their merits, where you have to use particular measure, and so on. Now, what is essentially lacking for the existing surrogate safety measure? So one of the main drawback of existing surrogate safety measure is that there is no information on the crash or conflict type that is happening, right? Because you know that there are different type of crashes, right? And none of the existing surrogate safety measure is not going to give you any information about the crash that is going to happen. Moreover, most of them are applicable only for certain crash type. For example, time to collision, it is defined for the car following condition. That means it will give you the crash risk of rear end crashes. It is not only the rear end crashes you can observe in a highway system. There is a lot more other type of crash types as well. For example, there is a head-on collision, side-side collision, and so on, right? And most of the existing, another drawback of the existing surrogate safety measure is that it captures either proximity or evasive action. That means either the surrogate safety measure capture only the proximity. It can be either in space or in time, spatial proximity or temporal proximity, or it will capture only the evasive action. No surrogate safety measure captures the combination of both spatial, temporal proximity as well as the evasive action. Now, I already discussed that different type of crashes you can observe in the field. Similarly, you can actually observe different type of conflicts. So there can be one conflict that will end up in the rear end crash. There will be one type of conflict that will end up in the side swipe crash. There will be another type of conflict that will end up in the run off road conflict. How are you going to quantify this conflict, and how are you going to classify this conflict? So this is one drawback of the existing conventional surrogate safety measures. There is no classification for the conflict based on the crash type, and we'll discuss why it is very important when we talk about some of the applications of surrogate safety measures. Now let me introduce the new surrogate safety indicator called anticipated collision time. So it is the temporal conflict proximity estimation considering most potential evasive action. That means it actually captures the temporal spatial proximity as well as the evasive behavior of the conflicting vehicles. So if you see the definition, it is similar to TTC, where it is the time remaining for a collision. In one sentence, if you say it is the time remaining for the crash if the interacting vehicles are not changing its state, right? But if you look into ACT compared to TTC, it is functionally different, meaning it is capturing the evasive action. So all the evasive action, including braking, acceleration, deceleration, speed, and steering rate, and so on. And also it is defined in the two-dimensional space compared to one-dimensional definition of time to collision, because it's in the car following state. And for the primary inputs for anticipated collision time are the shortest distance between the vehicles and the closing in rate between the interacting vehicles. We'll discuss this using these figures. But before that, let me make this statement. The closing in rate amalgamates all the state variables. Okay. So if you see these two, let's say these are two vehicles, and let's say at one particular time instance, the closest distance between these two vehicles be delta, and let the closest distance between the vehicles is coming down, or it is reducing at a rate of dou delta by dou t. Definitely after some time, the shortest distance between the vehicles will become 0, which means the crash has just happened, right? Now, anticipated collision time is nothing but the time for this particular process, which we can get from the difference of this width upon the closing in rate, right? Simple physics we are applying. That means we are getting ACT as the ratio of shortest distance between the vehicle at the time instance where we are estimating ACT and the closing in rate. So how we are going to define closing in rate? So if you see here, closing in rate actually captures the vehicle speed, vehicle acceleration, and the steering in rate of vehicles in the direction of shortest distance. So it is essentially the vector sum of the relative speed, relative acceleration, and relative steering of the vehicle. And as we discussed, ACT, if you take the ratio between the shortest distance and the closing in rate, you'll get the ACT value. And one condition for ACT to be valid is that the vehicle should be in collision course, meaning there should be a positive closing in rate. What will happen if the closing in rate is negative? A negative closing in rate means the vehicles are shying away, they are moving apart, right? So there won't be any crashes because the vehicles are going in an opposite direction. In that cases, we'll take the value of ACT as infinity, right? And if you want to know more about the anticipated collision time, you can go through this particular publication. And if you don't have the access, please let me know. You can drop an email to me. Now, once we extract the ACT value for the vehicles at every time instance, you'll be getting a profile something like this. Okay, so you can see a nice smooth profile of ACT for different vehicles. Each figure represents different vehicles, and yeah. Now, once you have this ACT profile, you can derive many other surrogate safety measures, namely time exposed to anticipated collision time, time integrated anticipated collision time, and so on. So if you want to do so, you need to define a threshold which actually demarcates the safe and unsafe regime for this ACT time plane, right? So similar to the previous slide, let's say this is the ACT profile, and we are defining certain threshold to demarcate the safe and unsafe regime. The time extended ACT is nothing but the duration for which the vehicle undergoes into unsafe situation within the total observation period. Okay, so if I take only this portion where the vehicles are within the unsafe regime, if I combine the TACT is nothing but T1 plus T2. T1 is corresponding to this, T2 is corresponding to this. Similarly, severity is the TIACT, which is actually the total area of the ACT, the total area between ACT curve and the threshold line. Okay, if you combine these two, this is the A1 and A2, the summation of these two is going to give you severity. Please note here that the severity here is not the crash severity. The severity we are getting here is nothing to do with the crash severity, which is the fatal injury crash or the property damage only. The severity here is the conflict severity. Higher the conflict severity, more likely the crash to happen. Okay, it can be a property damage only crash also. So this severity here is not the severity of crash. Please note that. Okay, so this is another important measure which we can derive from ACT, which is the time of evasive action. Because we already mentioned that ACT actually consider various evasive action that is happening. So once we have this ACT profile, we can identify the instance where the vehicle started to take any evasive action, for example, the deceleration, and to the instance of crash occurrence. Here, the crash means it is the conflict. The ACT will become 0, right? So the total duration is going to be the time of evasive action, or TEA. Why it is important? Because it gives an idea about how early a driver or vehicle is responding to a potential collision situation. That means if you have this information, you would be able to use it for defining the buffer time for giving the warning to a driver. Okay. So essentially, the meaning is that you can use the time of evasive action, the TEA measure, to effectively design the warning system with sufficient buffer time for the vehicle or the driver to respond. Now, we mentioned that if you want to do or derive all these measures, you have to define what is the threshold value, that is ACT star. So here we proposed a method called simultaneous optimization method, with which you would be able to project the proportion of conflict to the proportion of actual crashes. So this is not only the one approach available. There are several approaches to identify the thresholds. You can use optimization. You can correlate the crash and the conflict frequency. You can use extreme value approaches to identify the conflicts with certain assumptions. And also, this particular method has another benefit, is that suppose if you don't have the actual crash proportion, with the experience you can assume certain proportion, and you can identify the thresholds for the ACT profile. Or else you can try different proportion of crash occurrence, different type of crash occurrences, and you can see how or you can do the sensitivity analysis, how the safety is varying for different proportion of crash occurrences. Now, let me quickly show you some of the applications of ACT. The first one is powered two-wheeler safety assessment. Another, you can use it for safety at complex road geometry, such as 3D road geometry, where the horizontal curve superimposed with vertical alignment. You can use this ACT for identifying the hotspot on a transportation network and so on. So I'll not spend much time on this, because it is again about the statistics about the crash occurrence for involving the vulnerable road users. And this is the results when we did the analysis of comparison of PTW powered two-wheeler safety compared to other vehicle types. And similarly, we did the case study on the safety at 3D geometries, And one important point here you have to note down that the existing surrogate safety measures cannot be used for assessing the overall safety of 3D geometries, because we have certain surrogate safety measures for curved geometries which will capture only one particular type of crashes. Okay, and it is very important to do the safety assessment of such facilities because over 30% of the road fatalities are occurring at curves. And another important point is that 47% of the severe roadway departure crashes occurred on horizontal curves. And if you remember, I already mentioned that you can use this anticipated collision time to quantify the run-off-road conflict. And another important point, one interesting finding we could get after doing the detailed assessment of correlation of different geometric variables with the safety likelihood of crash occurrences, we found that different geometric element has contrasting correlation with geometric variables, which means that, for example, we found the curvature change rate is negatively correlated to the PET and positively correlated to the curvature change rate is negatively correlated to the TACT, and it's the for example, deflection angle is positively correlated to the TACT, the exposure time. So which means that if you are treating, if you are coming up with a geometric treatment or redesigning the highway to make sure that the crash risk is significantly reduced, let us assume that one particular crash is prominently happening at one particular highway, and if you are bringing with you're coming up with a treatment which is to resolve that particular crash type, it may end up with increasing the occurrence of other type of crashes, because we have seen that the geometric variable has contrasting correlation with the safety, right? Now, next one is the identification of hotspots on a transportation network. For that, we have used the NUMA data, which is collected in the Athens city using swarm of drones, having 10 numbers of drones, which was covering total of 1.3 kilometers square and more than 500,000 vehicle trajectories. So we use this data to identify the hotspots. So we did the spatial risk distribution of the traffic using the anticipated collision time, and you can see the high density area is the region where the crash or conflict frequency is very high. We can also map the severity and the exposure time for conflicts, and we can identify the locations where high severe conflicts and where the vehicles are highly exposed to crash risk. With this, I conclude my presentation. If you have any questions, please feel free to ask. Thank you so much.
Thank you, sir. That was an enlightening talk. Now the forum is open for discussion.
Morning, sir.
Hello.
Hello. Sir, I'm Shalini from NATPAC. Hello. Am I audible?
Yes, ma'am, it's audible.
Okay. I wanted to listen something more on the simultaneous optimization method that you were referring to for estimating the threshold by the simultaneous optimization method you were referring to for the threshold estimation. So, could you please detail on that methodology for doing the threshold estimation.
Oh, excuse me. I couldn't hear you because my device was mute. Can you please repeat the question?
Sir, I'm Shalini from NATPAC.
Yes.
I just wanted to get more light on the simultaneous optimization methodology that you were referring to for estimating the threshold.
Yes.
That is by mapping the estimated collisions with the actual that you were telling. I
Yes.
just wanted to know whether this estimation of the collisions, are you doing it by any simulation, or is from the modeling that we finally arrive at, we are estimating, and further correlating it with, I mean, mapping it with the actual. I just wanted to get a few little more details on this methodology, that is the simultaneous optimization methodology for this threshold estimation.
Yeah. Thank you for the question. It's a really wonderful question. I really appreciate that because if you see the literature, there is a lot of confusion about how to use the threshold value. And in fact, the current practice, if you see many of the literature, they arbitrarily choose the threshold value, citing some of the previous work. So with that, actually, we came up with this particular optimization method. In fact, it is a simulation-based approach. What we'll do is that for different iteration, we'll see a different level of threshold and try to see how the proportion of conflict we could get from the data we have is matching with the actual crash proportion. So the benefit here is that, because one of the major question might arise here is that people are already saying that there is a significant issue with the crash data. But if you go with the proportion of crashes, like what is the frequency of rear end crash, what is the proportion of side swipe crash, what is the proportion of angled collision, what is the proportion of ROR crashes, because of the law of large numbers, it will eventually the distribution will eventually converge to a constant value. The proportion will eventually converge to a constant value, which can be reliable compared to the individual data points. So with that assumption, we can take the different proportion of the actual crash occurrences, and we can bring this proportion back to the conflict data, adjusting the threshold. We can adjust the threshold to achieve what would be the threshold that is going to give you actual a proportion that is actually mapping to the actual proportion of the crashes. So that is the overall idea. It is, again, you're right, it's a simulation based approach, but we are not simulating it's an optimization approach. We are not simulating the conflicts. We have the field data of conflict information, which will be extracted using ACT. Now we are changing the threshold to identify the best threshold that is representing the actual field scenario. I hope I answered your question. If you have any further question, please feel free to ask.
Yes, sir. So what we are varying in, what will be varying in the simulation is the threshold value itself, rather
Threshold
than
value.
varying the other parameters involved. You'll be varying the threshold value, and we'll be seeing the effect of it. And finally, we should also have the data from the field also for that particular
Yes.
simulated scenario. Is
Exactly.
it like that, sir?
Yes,
Okay.
exactly.
Okay. Thank you, sir.
Yeah, thank you.
Hello.
Yes.
Sir, I'm Nanad Atle. Good afternoon, sir.
Good afternoon.
Sir, in one of the slides, sir, it was stated that 30% of the road fatalities occur on curves.
30% of the crashes are occurring on curves.
Of
Yes.
fatalities are occurring on curves. So can you just elaborate on this, like how we reach? It is a means for any road network, sir, for example, for any state. So
Yeah.
So is it a generalized means how we reach this conclusion, sir? Can you elaborate on this?
It's not a conclusion. It's a data which I received from, I forgot, I apologize that most of the references I couldn't add. It is from one of the studies, one of the reports I received. I got this data that most of the crashes that happens on rural highways, okay, so it's for rural highways. If you see the most of the crashes that is occurring on rural highways, it happens 30% of them are happening on horizontal cars. Okay. Yeah. So if you ask me whether it is going to be a constant value for all the countries, all the states, answer is it can vary. But the major point I would like to emphasize here is that majority of the crashes are happening on rural.
Hello. Sir, you are not audible to me. Hello.
Yes, you are audible.
Ma'am, you are audible, but I'm not able to hear what sir is saying.
Probably it's some issue at your end because it was audible to us.
Suvin sir?
Yeah. Am I audible?
Yeah, now it's audible, sir.
So now you are audible. So you were not audible for last 1 minute, I think.
Oh, okay. Okay. So my point is, the answer to your question is that if you ask me whether it is going to be universally correct, it is the particular percentage is applicable to everywhere. Answer is no. The point I like here is that the majority of crashes that happens on rural highways, you can see that horizontal alignment. It's the majority. That doesn't mean that all the crashes.
Because what we saw in the data that 90% was, again, the data quality is questionable, but they say on the straight, see, the speed enforcement is very weak in the states. So mostly there is overspeeding on straight alignments. And as for the accident recording agency is police. So mostly what the data we receive from morgues, so on an average more than 80% they are reporting as on the straight alignment as per the what we call the road feature type.
Okay. Yeah.
So,
I agree
therefore,
to that,
I
but
just wanted to know like if
highway. Sorry, please continue. Ninad, please continue.
So means if you have that some source, if you can tell, so what we can see, because even in the data that is being reported, so how road engineering factors are involved, that is not mentioned in, even in, if you look at the FIRs, like I am from Gujarat, so never ever a road related issue is being reported in the FIRs due to some, means there may be some obvious reasons for that, but so how road, means from the data it is not easily like as an engineer we know that what might have happened, but from the data like concretely saying that 30%, so means how we can also using that particular, so we can say that all these measures are important, so these need to be taken on therefore.
Yeah, I completely agree with you. I completely agree with you. So for your first point, maybe the highway type may be different where you collected data. If it is a straight kind of expressway kind of system, definitely it is going to happen most of the crash because of the. But this particular data, I think I would like to add one more point. Apologies for that lack of information. So this data is for actually the rural highways passing through hilly terrain.
Okay, rural
Okay.
For hilly terrain, yes.
Highways passing through hilly terrain. So maybe your facility type is slightly different. That could be the reason. And see, there is another concept of geometric design consistency. So if you think about it, there is a straight section and it's joining a kind of curve. Okay, let's say you can always see that on a straight section, the vehicles will be moving at a higher speed. Yes. And most of the on hilly terrain, if you see the design speed of a curve section is 40 to 60. Okay,
Yes.
so let's say the vehicle is moving at a speed of coming at a speed of 100 km per hour per straight section, and at the time when the vehicle enters the curve, there is a higher chance that this vehicle will run off the road, right? So that is the reason why we can see more number of crashes that happens near the curves. Okay, so if the curve radius is the curve radius is sufficiently large for your study area, then we can see most of the if we look into the proportion of the crashes, we can see most of the crashes happens at a straight section as well. But again, my point is it depends upon the facility type.
Okay. Thank
So
you.
the 30% which we mentioned is for the rural highways passing through hilly terrain.
And so I want to just share one observation, like now the sufficient IRAT data is available. So say for in our case from May 2022, the accidents are being recorded on IRAT. So now what we are seeing is that on bypasses are very much vulnerable because there are interactions of like different types of vehicles, say two-wheeler riders and specifically and large vehicles. So what we are seeing that on city bypasses, so a lot of fatalities are occurring. This is so what you would like to say on this? This is what we are seeing. Like just we have a partial snip of that IRAT portal. So what we say in big cities, say Surat, Ahmedabad, Bhavnagar, so especially the bypasses are very much vulnerable, and we think due to the because there is interaction between large vehicles and the VRU and especially the two-wheeler riders. So this is the
Yeah, see, I mean, if you ask me this question, the answer is straightforward. We all know the answer, because if the interaction is the problem, if the interaction between the two-wheelers and trucks or the heavy vehicles problem, we have to provide dedicated lanes for two-wheelers, right? That is the straightforward problem. But unfortunately, the issue is not that, it's something beyond that, right? We need a lot of educational awareness program we have to bring, and also if it is something related to highway geometry, definitely we have to identify and we have to come up with solutions for that. And ultimately, when we design service in terms of transportation services, we have to make sure that the highway is forgiving, right? The drivers are human beings, right? They are of course they'll make mistakes. So the design itself should be forgiving in such a way that minor mistakes will not end up in a severe crashes. So one solution I can suggest you is that we can actually collect the config data from the field, and we can identify what particular element or which link of this entire crash generation process is more critical, and try to break that with some safety treatment. So that is the straightforward safety improvement approach. If you are using a approach, but you have enough crash data, you can always go with the safety performance function, and you can compare the safety performance function for different treatments, and you can see whether the facility is giving adequate safety or not. And it's a very, very good observation. I must really appreciate that. Thank you.
Thank you, sir. Thank you so much.
Good afternoon, sir. A couple of questions more. Sir, you were referring to a swarm of drones used for the identification of hotspots for a road network. There, the identification was based on from the drone videos. Was it based on the SSM measures, or was it based on the actual number of hits or collisions that has taken place during the period of observation? How the mode of conduct of that identification was carried out?
Okay. Yeah, so this data, the NUMA data, very recently released by the EPFL University in Switzerland from the group of Nicholas Gerolimus. So what they have done is that they have used 10 drones simultaneously flew over the ethnicity, and they outsourced it to extract the vehicle trajectory data. So ultimately what they have is the vehicle trajectory data. So once we have vehicle trajectory data, which will include the vehicle position, vehicle speed, vehicle acceleration, and so on, right? And this vehicle trajectory data is, in fact, is the input for ACT estimation. So once we have the vehicle trajectory data at every time instance, we will be able to estimate ACT. ACT is nothing but a surrogate safety measure, which will help you to identify the conflicts.
Okay,
So this time series information of the ACT, we identified the conflict using certain threshold.
okay.
The threshold identification was based on, for the ethnicity, they have the crash report and the aggregate is already available. So based on that, we estimated the threshold value and mapped it for estimating the hotspots. Did I answer your question?
Yes, sir. So the trajectory of the whole vehicles, whole number of vehicles that were flying on the roads were being extracted, and real-time process is being carried out for identification.
Exactly. Yes. Yes.
And one more thing,
Yes.
sir, for we have a palette of SSM measures available for the proactive assessment. So depending upon the type of collision, is it like that that we have to choose the appropriate SSM based on the type of collision, or how do we actually make a a trade-off between these different SSM measures for the appropriate assessment of proactive assessment for the different kind of collisions? Is it collision specific, or what are the criteria to be applied for that appropriate selection?
Yeah, good question. So here one important point we have to keep in mind when you do this priority safety analysis is that let it be rear end collision, let it be side collision, all the collision types are important, right? What we have to quantify the overall crash risk. Now the problem with the existing surrogate safety measure is that it may not capture one particular type of collision. For example, using time to collision as a surrogate safety measure, it's not going to capture many other type of collision. It is going to capture only the rear end collision. That means you are only capturing the crash risk corresponding to only rear end collision, and it's not going to tell you what is the crash risk associated with other type of crashes, right? For example, I'll give you a good example. When we are doing the priority safety analysis for this curve section itself, we found that the rear end collision on a horizontal curve is just 10%. That means if you are using time to collision measure to quantify the crash risk, you are able to capture only the 10% of the overall crash risk. So you have to use certain surrogate safety measure which can holistically capture overall crash risk. But see, I mean, again, if your objective is to understand one particular crash risk, then it is okay to use one particular surrogate safety measure which can capture that particular crash risk. But if you improve the crash risk of a facility, you should be able to capture the overall crash risk for the facility. So if you ask me what is that particular surrogate safety measure which can capture all the surrogate safety measure, all the different type of conflicts, now I know only ACT can capture that compared to any other existing surrogate safety measures.
Which one, sir? Could you repeat it?
The anticipated collision time.
Okay. So that way it is becoming more advantageous over the others.
Yeah. Yes. So when you process the trajectory data, so we have a tool for estimating the ACT value. If you input the trajectory data, it is going to output a file and it is going to give you the instantaneous, the time series information of ACT values along with what is the conflict type it is. So every time instance you will have an ACT value and the corresponding conflict information, what type of conflict it is. So the output of this ACT analysis is something like that. So you can actually sort or filter different conflicts, or you can combine all the conflict type to understand the overall crash risk, and also use you can filter out different conflict types to understand individual risk of one particular crash type. Yes.
Thank you, sir.
Yeah. Thank you so much.
I request Dr. Praveen P.S., Junior Scientist, Transportation Planning and Execution, to propose the vote of thanks.
Good afternoon, everyone. So on behalf of KSCSTE-NATPAC, I'd like to extend my heartfelt gratitude to each one of you for joining us today for this insightful technical talk on the topic, revisiting proactive road safety analysis, past, present, and the way forward. It has been an enlightening and thought-provoking session, shedding light on the proactive assessment techniques, benefits of proactive assessment over active safety assessment, and desirable properties of surrogate safety measures. First and foremost, I'd like to express my sincere thanks to our esteemed speaker, Dr. Suvin P.Venthuruthiyil, whose expertise and knowledge has truly captivated our audience. Thank you, sir, for delivering an engaging and informative presentation backed by thorough research and practical insights. We are grateful for the knowledge and insights you shared with us today. I'd also like to thank all the attendees who have joined us today and blessed us with their presence in making this a successful event. The questions and discussions that followed the talk showcased your deep interest in the subject matter, and I commend your engagement. We are very much thankful to Director NATPAC for his constant guidance and support in shaping this wonderful event. Finally, I would like to thank our division heads and the organizing team for their meticulous planning and coordination that made the smooth execution of this program. In conclusion, I believe we have all gained valuable insights from today's technical talk, deepening our understanding on doing proactive safety analysis using anticipated collision time. Thank you once again to everyone involved, and we look forward to hosting more technical talk in the series and continuing this legacy. Thank you all.
Thank you, Suvin.
Thank you so much.
Yeah.
Yeah.
We'll catch up sometime. I'll operate through
Definitely.
Vasu. Okay.
Definitely. My pleasure. Thank you so much. Bye. Take care. Have a great day.
Thank you.
Thank you.